Hi, I want to talk to you about a new operating system that we've been building at Cornell called the Nexus. And in particular, I want to talk to you about its authorization architecture. Now, the first question you might have is, why revisit authorization? And the answer is very simple. We have new hardware in the form of trusted platform modules, that is, secure hardware coprocessors that are manufactured with a unique key on board and a set of cryptographic facilities that can actually provide some kind of a trustworthy statement about the state of software at a remote machine. Now, this is a groundbreaking new capability. And furthermore, the devices are cheap. They can be manufactured at the cost of just a few dollars. And they're rapidly becoming ubiquitous. My laptop certainly has them. Most of your laptops probably have them as well. And the third and most important part is they have the potential to be truly evil. And in particular, the source of this evil has to do with the hardware interface that the TPM provides. The particular hardware interface that is easy to implement, it is in fact probably one of the only tractable way of doing this, is by providing an attestation certificate, a certificate to the state of software that captures the binary hash of the components that have booted on a machine. Now, this kind of hash-based attestation has a number of drawbacks, and the root cause of the drawbacks has to do with the way that it forces the users of these certificates to do authorization. In particular, hash-based certificates force the users, force the consumers of these certificates to have to make a decision based on axiomatic trust. That is, you trust the software because it has a particular hash. And what this then implies is that the user must be running software with the particular hash you have in mind to satisfy your security policy. This, of course, eliminates user choice and restricts control over the platform and takes it away from the user and entrusts it to remote entities. There are, of course, a bunch of, this is the major problem. There are, of course, a bunch of sort of side effects as well of this whole axiomatic trust. It requires for the person making the trust policy decisions to retain and keep up to date a set of binary hashes corresponding to configurations that they trust. And this is not a trivial task. Further, the attestation process based on binary hashes requires the software, the local client, to reveal its software state. And in doing so, you might be actually telling the world or telling a remote party that you actually are running an out-of-date version of software and might actually be might be running with the vulnerabilities. And it does not, lastly, it does not necessarily capture the dynamic state of the program, that you end up making trust decisions based on the binary hash, you end up making trust decisions based on the binary hash and not necessarily on the dynamic configuration. So, for example, if you're running Internet Explorer, it's possible to run it in a configuration where ActiveX is disabled, where it may be trustworthy. But because it's possible to expose some path through that code that is not trustworthy, it's difficult for a remote party to ascertain whether or not you actually have it in that state. The hash does not capture the dynamic runtime state of the program. So I'd like to posit to you that in the real world, we have other means of establishing trust besides trust by by axiom, trust by fiat. So trust by fiat, in a sense, corresponds to the way we authorize, say, the flight marshals by checking to make sure that the way they look matches the IDs that they carry. But there are other ways of entrusting users. So, for example, analytic trust is implied whenever somebody uses an analyzer to test properties of software. So type checkers, binary analyzers, and so forth can give you certificates that say that this code only contains forward jumps, for example, and is thus guaranteed to terminate. Or that code is type safe, and therefore it will end up performing only those operations that provide type safety guarantees. So this is similar to the way we make sure that you are safe to board a plane because you've been checked and you're not carrying any weapons. Another way in which, in the real world, we establish trust is by synthesis. That is, we make sure that not only that a program is We make sure that a person boarding the plane is not only not carrying any dangerous weapons, but is also actually shielded from the cockpit by a thick door. In the computer world, this corresponds to tools like reference monitors, sandboxes, SFI, and binary rewriters that can actually make sure that the code is executing in a certain environment where it cannot issue certain system calls or it has to respect certain resource limits. So authorization, in the end, will end up coming down to a simple if statement. That is, should this principal be allowed to perform this operation on this resource? But how that statement is implemented has profound consequences. It has consequences on what kinds of policies you can express, how practical the system is, and what kind of performance it will achieve. So the impetus behind our work was to come up with an authorization architecture that could support all three means of establishing trust. And today I'm going to talk to you about logical attestation, which is a new attestation scheme that doesn't just capture the syntactic binary hash of a program, but captures the semantic properties of a program, and it allows you to make a decision on whether or not you trust some code because the code is capable or is not capable of doing certain things that are of importance to you. I'll briefly outline the structure of the Nexus OS and talk about the mechanisms it has for generating meaningful and useful credentials, for managing these credentials, combining them with dynamic operating system state, and for checking these credentials efficiently. And we've built a large number of applications for this OS. Today I will have time only to talk about just two of them. So the central concept, the central abstraction behind logical attestation is that of a label. A label is a simple statement attributed to a principal. In Nexus, these labels are uttered by a labeling function, which could be any program. They're unforgeable, backed by a TPM, and they're expressed in a variant of first-order logic. The particular logic that we use is called Nexus authorization logic. This is a new logic that we developed. It's similar to CDD and ban logic, so it has says and speaks for, the familiar constructs that you might have seen. Being a logic, it's machine parsable, and therefore it's amenable to all sorts of tools that can use the machine-emitted labels for analysis. The logic itself is extensible. The terms defined by the logic are defined by the label producers themselves. We as OS designers do not impose any kind of nomenclature or terminology or any kind of semantics on what people are uttering. So type safe, the word type safe for a Java analyzer might mean something, for a C# analyzer might mean something else. The interpretation is up to the producers and consumers. This allows the logic to be extensible. And the logic can incorporate references to dynamic system state. In particular, it can refer to OS state, and I'll talk about how this is done in a second. It's a constructive logic. In a constructive logic, all reasoning and all deduction requires positive evidence. In particular, what that means is the absence of a label, the absence of an utterance cannot cause a principal to take some action to allow some authorization to proceed. And this is crucial for an operating system because the denial of service attack cannot be escalated into an access attack. It's a logic of beliefs. So now allows every principal to have its own worldview about the set of statements it believes in. This is a crucial property for a logic to have that's going to be used in any practical setting. What this means is that there is failure isolation between entities that will be emitting statements, and a badly constructed principle will not taint the worldview of other principles that don't trust it, will not cause somebody to take to make false or illegal deductions. And finally, now provides sub-principles and groups in addition to primary principles consisting of keys and processes. And the sub-principles and groups are crucial in an OS setting because they capture the dependence between entities like processes and operating systems and platforms and so forth. So just to show you what this looks like, a label for an axiomatic that's going to be used in an axiomatic decision might look like the first one that's shown on the slide here. So here user EGS says some hash speaks for him. This is a simple delegation label. An analyzer might emit a label that says that it has deemed an application to be type safe, and it looks kind of the way I showed here. It's up to the consumer of this label to decide what that type safe word means. And similarly, a reference monitor might say that a particular process with a certain PID has, say, in this case, no access to the disk. And the labels allow us to capture utterances of this kind. Now, keep in mind that, that anytime there is any principal here, that principal's execution is dependent on a set of other software that's running. In particular, it's dependent on the OS that executed that particular labeling function. And that OS's integrity is then dependent on the bootloader and so forth. This is the standard secure boot material. And I will not be showing the entire chain here, but all of our certificates capture this dependence chain. So labels in Nexus are issued into label stores with a new system call, the say system call. And the process is fairly simple. And because there exists a secure channel between the speaker and the kernel, the process of emitting a label does not necessarily imply use of cryptography. So our labels are not signed unless necessary. Now, the labels can be externalized and if desired. And when that is called for, then we actually convert them to X509 certificates with full crypto signatures. They can be internalized, copied, deleted, and so forth, and managed in the label store as one would any other kernel resource. The Nexus enables all resource accesses to all system resources, including files, IPC channels, sockets, and so forth, to be predicated on a guard. The guard performs authorization by checking labels against a goal formula. So a goal formula is a simple statement that has to be discharged for access, and it can capture any provable characteristic. So a new system call called setGoal allows someone to set the desired goal for access to that resource. And of course, setting the goal statement itself requires authorization. And there's a little trick that we do with to ensure that nascent objects are not exposed to people who might come in and try to set a goal on them. And in that case, only the creator of initially only the creator of an object can set the goal. There's no super user in Nexus. It's entirely up to the creators of the objects to set the goals as appropriate. Now, we have these guards. The guard's job is to guard the goal formula, as I mentioned. And the clients then have to generate proofs that discharge the goal formula. The guards validate these proofs, and in doing so, they might have to consult authorities. So in this case, we have a guard with a goal formula. We have a number of labels, and our job is to create some kind of a proof that says that we can discharge that particular goal formula. I should be able to go through the door because I'm a faculty member, and it's between 9 and 5, and and the person who says I'm a faculty member has been delegated by the provost, who's been delegated by the president, and so forth, and therefore, open door. Now, these authorities are called for because certain statements are time-varying and non-monotonic. This is an area where a number of previous systems that tried to do credentials-based authorization or proof-carrying authorization went a little overboard with the logic system, and ended up relying on the logic to carry all information. In an OS setting, we found that the OS typically contains state that we need to refer to, and that state is time-varying. So the time changes, for example. The number of times a file has been read or accessed, that changes. Current memory consumption changes. It's not sound to issue a statement that says the number of files, this number of times a file has been read is 3. It could be invalidated the second after you issue that statement. So in logical attestation, the validity of time-varying labels is checked by consulting an authority. And authorities are designated by the goal formula, and multiple authorities can coexist. So you can trust NTP, and I can trust US Navy time, and that's totally fine. So just to briefly recap, to get access to a Nexus resource, the owner sets a policy and says set goal is that the file says time is less than 3 p.m. User gathers labels and generates some kind of a proof, and guard verifies the proof and labels, and then decides whether the goal formula is discharged. Now, if that was the whole story, it would be incredibly slow. So we use caching throughout the system. In particular, we use a decision cache inside the OS to keep track of proofs that we have recently checked that have not changed, that could be reused. So if you're reusing the same proof over and over again, we don't have to incur the same cost more than once. A user-level guard cache sorry, the decision cache avoids re-invoking a guard. And we have another cache inside the guard that avoids revalidating portions of proofs. So let me just show you this pictorially. I think that's a lot simpler because I needed a lot of mechanism just to get to the point where we can do something useful. So this is what the process kind of looks like. In a simple operating system, naive operating system, we would have a caller invoke an object, and it would just go through the kernel. The kernel would have some static ACL or CList or something of that kind, and it would do its authorization in the usual manner. In the Nexus, the caller goes into the kernel. There's a decision cache that's consulted to see if we've seen this particular principle with this subject, with this method, with this proof, and whether or not the goal has changed in the past. If the decision cache, in this case, is going to be empty, there's not a hit in the decision cache, we consult the guard. The guard contains the proof checker, and in checking the proof, it might consult a label store to see if the labels supplied by the caller really exist, and it might actually consult a number of authorities about time, about other system state. And getting back the responses, it then populates its own proof cache and decides whether or not the process should go forward, whether the goal formula has been discharged, and if so, the access continues on. So this is the basics of authorization with proofs in the Nexus operating system. I want to now tell you a little bit about the OS itself, because this particular underlying structure is useful, but it's not sufficient to build the kinds of applications we'd like to build. The Nexus itself is a microkernel. It's only about 21,000 lines of code. We reduced the kernel size mostly by taking the device drivers outside of the kernel and running them in user space. The system is somewhat POSIX compatible. We left out the complicated stuff, but we have sufficient support to be able to run Python, LightTPD, SQLite, MPlayer, and a bunch of other applications. Until recently, we could run Zen, and in fact, even Linux on top of the Nexus. Then we broke it. It's currently broken. Let's see. The Nexus provides a number of non-standard services. I gave you a glimpse of the labels, label stores, guards, and authorities that we support. I want to next talk about two other services of the three extra ones that we have, Introspection and Interposition, because they are very useful for building applications that utilize analytic bases and synthetic bases for trust. So some analyses simply involve examining an application. And for these, we don't really need any system support. If you've got a binary checker, you can just go check the binary of an application. But there are many analyses that we've found that actually are asking questions about the state of or the environment in which the application is running. They might ask questions about, for example, which IPC channels are connected to which entities, what kinds of resources this application has, what kinds of resource reservations the kernel has granted to this application, how much memory it has, and so forth. So to support this, we have a /proc file system on steroids, in essence, where the kernel exposes all this kind of state up to the labeling function. Of course, in doing so, it still enforces authorization, so the application controls how much of the state a labeling function sees. In addition, we have an interpositioning service where there's a new system call that allows an interpose system call that allows a reference monitor to come between an application and the kernel. And by doing so, these reference monitors can mediate the system calls emitted by the application and thus change and modify what the application is doing with the outside world. So let me give you a glimpse of two applications that we built on top of this. One of them, we tried to pick some challenging applications. And one question that we asked was, what if Stallman was running a content distribution service, say Sony, and he wanted to make sure that his content would not leak, but he doesn't want to restrict the user's choice in what binary to run. Remember that with traditional hash-based attestation, Sony would say you should be running, say Microsoft Media Player 10.4, and you just need to run that particular binary. Well, with this setup, what we can do is the following. Stallman can write a labeling function. That labeling function gets shipped to your Nexus box. Labeling function is free to perform analysis. It's also free to install reference monitors, if your application, of course, allows these things. And after doing so, it can actually issue some statements to you that says something like, this application is one that I've analyzed, and it lacks the ability to write to the disk or the network. And these labels can then get shipped to remote parties, and they form the basis for a proof that might then discharge somebody whose policy is, don't leak my data, but I don't care what media player you use. I want to also tell you about a different demanding application where we looked at, that we call Phobok. And we looked at essentially privacy-preserving social network applications. So in this setup, we have three classes of principles. We have a cloud operator on which cloud application developers, like Phobok developers, deploy their applications. And then we have users of Phobok. Now, there are a number of guarantees that one would like to issue in a cloud environment. So the paper has the details on the resource side of things, where the cloud operator can guarantee to the cloud application developer that she will receive a certain level of resources. So, for example, the amount of CPU cycles that a user will receive is not one that's based on reputation. It's not something you do by trial and error, but you actually receive a certificate from the underlying Nexus OS that says that you really have only so much oversubscription to the CPU on this host. I want to talk a little bit more about the second assurance, which is that in our case, we're able to provide assurance to users of the cloud application that their data will not leak beyond their social circle, even if the developer is adversarial. That is, the developer is out to get their social networking data, and yet we will protect the user from them doing so. So the insight behind this approach is quite straightforward. These applications tend to be data independent. That is, it's possible to implement the core data sharing functionality found in a social networking application without examining the data. So the core mechanism that I'll be showing to you is some kind of a reference monitor that's going to wrap all incoming data into a Python object that's going to be opaque to the applications. The applications may slice, dice, concatenate COBUFs, these constrained buffers, to generate the pages that the users see, but without the application developers seeing that data themselves. And we're going to be utilizing all three bases of trust: axiomatic, analytic, and synthetic. And I'm going to do this informally because the number of labels is actually quite large in this example. But I just want to go through this very quickly and show you the types of guarantees that we can get. So in Phobok, the driver needs to assure the user that it's not going to steal the user's data as it comes off the network and divert it elsewhere. And it's very easy to do so because our drivers run in user space and they're constrained by a device driver reference monitor. And the driver can easily show that it actually lacks write access and can only ferry data from one source to another single source. In this case, the network driver shows that it's connected to LightTPD and nobody else, and therefore the packets are destined for LightTPD. The LightTPD web server, now this is the one part where we were not clever enough to come up with a good way of ensuring trust in LightTPD. We relied on axiomatic trust because LightTPD actually manipulates packets. It changes IP addresses and so forth. It needs read and write access to packets. Luckily, LightTPD does not change much, so it's possible to just assure LightTPD once and then gain trust in it by a binary hash. Now, let's take the Phobok application, where the developer wants to take the data that you submit and perhaps use it for other purposes. You can take your application and run profiles on you, sell it to advertisers, and so forth. Well, before this code is injected into the cloud, an analyzer checks that it does not use Python reflection or any other mechanisms to violate the COBUF interface. So you cannot go around the type system to try to peek inside the opaque COBUFs that we're going to be generating in a second. So we simply ensure through an analyzer that Phobok is written in a sort of well-behaved manner. From then on, as applications send in packets, they create a particular social network graph, and these are handled by some kind of a module that actually provides the database for this operation. And at the end of the day, the critical step happens with user-submitted data. Whenever a user submits some kind of, in this case, a picture, the COBOF module simply wraps the picture in a COBOF, which turns it into an opaque object and passes it up to Phobok. Now, Phobok can do whatever it wants with this, but it cannot look inside and say, and reuse my picture in some advertising that it's got. So here's some update from a friend of mine. And each of the COBOFs, of course, is tagged with the source of the data that it came with. In this case, it's colored, blue or yellow. And when it's time for Phobok to create a page and show it to somebody, it can do so by putting together these opaque blocks. And, but it cannot send these out without to anybody who's not authorized in the social database on the right-hand side. And while these packets are actually destined on their way out, they get de-opaqued, I guess, and the actual contents are visible to whoever has been authorized to see them. Okay, in terms of evaluation, I just want to mention that I just want to show you one micro benchmark and one macro benchmark. So proof-carrying systems or proof-carrying authorization can be slow, but in our case, it mostly has been, the overheads have been modest. So Willem de Bruyne has done a pretty good job of engineering the core system such that our protected calls are about the same cost. In this case, get PPID is the call to look at. Our protected calls are about the same overhead as a regular Linux call. In the case in the sort of more complicated benchmarks where open, close, read, write, and so forth, we're a little slower because our file system is not inside the kernel. We have to bounce up, back, down, and up out of the kernel. And and I want to show you just this benchmark where essentially the takeaway is simply that cache decisions incur a cost only of less than a microsecond, just about 450 cycles or so. Guard invocations are a bit more expensive, but they're actually quite rare in our system. There's a lot of related work in this space. I will not go through it. I know that I'm standing between you and lunch. But I'd like to conclude by saying that TPMs can be used to build the next generation of trustworthy applications. Their use need not impinge on the user choice over software, client software. And they can provide qualitatively richer guarantees if we were to wrap a different abstraction layer on top of the binary hash-based attestation primitive they provide. And there's a lot of future work based on creating novel applications, creating novel labeling functions that we haven't even thought of to enable different kinds of guarantees. So with that, I'll take questions. I guess I should mention one other thing. If you wanted to pull out the code, it's on Git, and if you want the project webpage, it's up there.